For centuries, some of the greatest minds in history, Albert Einstein, Stephen Hawking, and many others, have pursued one of the most ambitious goals in physics, the search for a theory of everything. This elusive theory aims to unify all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, all-encompassing framework. Einstein spent the final years of his life searching for this grand unification, but the challenge proved far more complex than even he had imagined. Later, Hawking continued this quest, exploring ideas such as black hole radiation and quantum gravity, hoping to bridge the gap between general relativity and quantum mechanics. However, despite incredible progress in physics, the unification of all forces remains an unsolved mystery. What if we could finally crack the code of the universe? A theory of everything would offer the deepest possible understanding of reality, explaining everything from the behavior of subatomic particles to the formation of galaxies. It could revolutionize technology, cosmology, and even our philosophical perspective on existence. So, how close are we to finding this ultimate theory? What challenges stand in the way? And what would a successful theory of everything mean for the future of science and humanity? One of the most ambitious and far-reaching goals in modern physics is the pursuit of a theory of everything, a framework that unites all fundamental forces of nature into a single, coherent model. This elusive theory seeks to explain gravity, electromagnetism, the strong nuclear force, and the weak nuclear force under one universal set of principles. If achieved, it would provide a complete understanding of the universe, bridging the gap between the smallest subatomic particles and the vast, cosmic structures that define our reality. Currently, our understanding of nature is based on two powerful, yet fundamentally different theories. Quantum mechanics, which describes the behavior of subatomic particles like electrons, quarks, and photons. General relativity, which explains gravity and governs the large-scale structure of the universe, including planets, stars, and galaxies. While both frameworks have been remarkably successful in their respective domains, they remain incompatible with one another at a fundamental level. The quest for a unified theory stems from the need to reconcile these two cornerstones of physics into a single model that works seamlessly at both microscopic and cosmic scales. Bringing together quantum mechanics and general relativity into a single unified theory is one of the most difficult problems in physics. Several key challenges make this endeavor particularly complex. Conflicting mathematical foundations. Quantum mechanics operates on principles of probability and uncertainty, where particles can exist in multiple states simultaneously until observed. In contrast, general relativity describes gravity as the smooth curvature of space-time caused by mass and energy. These two frameworks rely on fundamentally different mathematical structures, making it difficult to merge them into a consistent theory. The problem of quantum gravity. One of the biggest obstacles is formulating gravity within a quantum framework. General relativity treats gravity as a continuous field, whereas quantum mechanics explains forces through discrete particles, known as quanta. When physicists attempt to describe gravity in quantum terms, they often encounter mathematical inconsistencies, such as infinite values that defy physical interpretation, a problem known as renormalization. To fully unify these theories, scientists must understand the universe at the Planck scale, an unimaginably small length of approximately 10 to the negative 35th power meters. At this scale, both quantum effects and gravitational effects become equally significant, meaning our current understanding of space-time itself may need to be revised. However, exploring this realm experimentally is nearly impossible with today's technology, as distances and energy levels at the Planck scale are far beyond our current reach. While quantum mechanics and general relativity have been extensively tested and confirmed in their respective fields, particle physics and cosmology, there is still no direct experimental evidence supporting a unified theory. The extreme conditions required to test such a theory, such as those found in the early universe, black holes, or ultra-high energy particle collisions, are incredibly difficult, if not impossible, to replicate in a laboratory setting. These challenges highlight why the search for a theory of everything remains one of the greatest unsolved puzzles in modern physics. Over the years, several compelling theories have emerged in the quest for a theory of everything, each offering unique insights while facing its own set of challenges. String theory. One of the most widely studied approaches, string theory proposes that the fundamental building blocks of the universe are not tiny point-like particles, but rather one-dimensional vibrating strings. The different vibration patterns of these strings correspond to various particles, including photons, electrons, and even gravitons, the hypothetical quantum carriers of gravity. While string theory presents a promising path toward unification, it relies on the existence of extra spatial dimensions beyond the three we experience, and so far, it has not produced testable experimental predictions. Unlike string theory, loop quantum gravity does not require extra dimensions. Instead, it suggests that space-time itself is quantized, composed of discrete units or loops woven into a fundamental structure. Loop quantum gravity aims to integrate gravity into quantum mechanics by treating the fabric of space-time as a dynamic, quantized entity. However, this approach is still in development and has yet to produce concrete, testable predictions. M-theory. An evolution of string theory. M-theory seeks to unify the 5 different string theories into a single, comprehensive framework. It introduces higher-dimensional objects called branes and incorporates ideas from supergravity. A key implication of M-theory is the possibility of a multiverse, where different universes could exist with their own distinct physical laws. Quantum field theory and the Standard Model. The Standard Model of particle physics successfully describes 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, using quantum field theory. However, it does not incorporate gravity. Efforts are ongoing to extend quantum field theory in a way that seamlessly integrates gravitational interactions, bringing physics closer to a true theory of everything. While none of these theories have been fully validated yet, they represent critical steps in the ongoing effort to unlock the fundamental nature of reality. If physicists were to uncover a theory of everything, it would fundamentally transform our understanding of the universe, with profound scientific, technological, and philosophical consequences. A successful theory of everything would merge all fundamental forces and particles into a single, all-encompassing theory. This would bridge the gap between quantum mechanics and general relativity, providing a coherent model that explains everything from the smallest subatomic particles to the largest cosmic structures. With a theory of everything, we could gain deeper insight into the Big Bang and the earliest moments of the cosmos. Understanding how forces interacted at the most fundamental level could reveal how the universe came into being, how it evolved, and how complex structures, galaxies, stars, and even life emerged. Just as discoveries in electromagnetism paved the way for electricity, communication technologies, and modern computing, a theory of everything could usher in entirely new fields of science and engineering. This might include revolutionary energy sources, advanced space exploration methods, and breakthroughs in quantum computing that exceed today's capabilities. A theory of everything would likely introduce entirely new concepts, such as unknown particles, hidden forces, or extra spatial dimensions. It could solve long-standing mysteries, including the nature of dark matter, dark energy, and quantum gravity, providing a clearer picture of black holes and the structure of space-time under extreme conditions. A true theory of everything might redefine our understanding of reality itself. It could answer fundamental questions about the nature of existence, the possibility of a multiverse, and whether the laws of physics are absolute or vary across different realms of reality. It may even shift our perspective on humanity's place in the cosmos, raising new questions about the fundamental nature of consciousness and existence. A theory of everything wouldn't just be a scientific breakthrough. It would be a paradigm shift, redefining how we perceive the universe and our role within it. The search for a theory of everything is more than just a scientific endeavor. It's a journey to uncover the fundamental laws that govern existence itself. From Einstein's dream of unification to modern advancements in string theory and quantum gravity, we are slowly piecing together the puzzle of reality. Yet the final answer remains just out of reach. Will it come from a breakthrough in mathematics, a revolutionary experiment, a new way of thinking about space and time? The path forward is uncertain, but what is clear is that every step brings us closer to understanding the deepest mysteries of the universe. Perhaps one day, a theory of everything will not only redefine our knowledge of the cosmos, but also open the door to technologies and discoveries beyond our wildest imagination. Until then, the quest continues, pushing the boundaries of what we know and challenging us to rethink the very nature of reality. Thank you so much for watching and listening. The video is over. Goodbye.